You got it? You got it? All right, I'll begin. Dear Heavenly Father, we thank you for this day. We thank you for the summer, just completed, all the rest and relaxation. Just pray that you just guide this class this semester, that you bless it, that whatever we do, Lord, here, it be for your glory, Lord. In your name I pray. Amen. So it's good to see some of you back. I'm sure you're eager to get ready and just get started and get into things. I am too. Here's the roster. You can sign it if you're here. If you're not, please don't sign it. I will tell you this. I was watching the news this morning, as I sometimes make the mistake of doing, and I think it was Today's Show to be specific, and they had this rather unpleasant news story about how they said that there's a study that showed that the amount people learned was directly proportional to the attractiveness of the instructor. And I thought, I didn't care for this. I don't care for that at all. I just thought that was... I mean, I just don't like that. Doesn't seem right. So of course, this is a course in abstract algebra. And I'm just going to get straight to it. The syllabus is online. We have 3 tests. The date, that's there. There's a homework at the end of this lecture. There's 4 problems I've assigned that I'd like to collect Friday. They're not that hard, so hopefully you can do them. You need the textbook. The notes that I write this semester will be pretty fresh. I've typed these up in the last couple days. So, that actually does improve the quality of my lectures, I find. That's not entirely the reason for doing it, but it's a side benefit for you guys. So the lecture notes will be posted as the semester progresses bit by bit. And hopefully I won't edit what I've already posted that much. I mean, I might find a grammatically horrible sentence that I just can't leave or something. Or maybe you can say, Dr. Cook, this sentence, it's just fix it. It's bothering me. And if you ask me nicely, I might do that. There are, it's kind of like the Batman versus Superman movie, you know? Like the general idea of it's pretty good, but there's some awkward lacks of continuity here and there. Anyway, okay, getting back to the real story here. So group theory, right? What's group theory about? Why do we study group theory? What's its origin? That's the thing I want to talk about today, and just show you a few elementary things about it. So I suppose the story goes back. This is the start of the story. Well, how do you solve this? Ax squared plus bx plus c equals to 0. I think most of you can tell me the solution to that, right? If you want real solutions, how do you find them? You look for what? X equals to, you know it, minus b plus or minus square root of b squared minus 4ac divided by 2a, right? So who discovered that? Or invented it? I think nobody knows. It's pretty ancient, right? Yeah, Babylonians, people who are long since dead. So that's pretty old, right? Much more recently, since the 1500s, we've known about how to solve things like this. So this is a cubic, right? So the cubic equation, a solution to that was also in terms of a nice formula like that quadratic equation. This is apparently due to a few different people had things to do with it. There's this guy named, I gotta look at my notes because I don't remember the spelling otherwise, Tartaglia. These guys got great names. There's this Tartaglia dude, Del Faro, I'm sure I'm saying that wrong, Cardano, his student Ferrari. It's an awesome name. So Tartaglia and Del Faro, Cardano, all these guys had something to do with solving the cubic in the 1500s. In 1545, there's this work, the Ars Magna, where, in fact, they took it a step further. In fact, this Ferrari character, he solved the quartic as well. And that was published in this Ars Magna. So it's about a half a millennium ago, right? So that's, Now, didn't make it to the notes, but I was reading a little bit more. Maybe Archimedes knew how to do this too. It wouldn't be that surprising if really brilliant ancient engineering types could solve cubics, all right? It's still, it's much harder than that, but there's hope. I'm not going to write the formula for the cubic for you guys, okay? I have a link in the notes. Lorenzo, you'll be delighted. These notes are very, very footnote. 7 pages of notes, 21 footnotes. You will not be disappointed. So I know you asked for footnotes, so I've done my best. Now, so this is the cubic. And, if you look at, I think if you look at some of the work that, for example, Euler and Lagrange, a little bit later, these guys are, 17th century. They took Lagrange, the late part of the, 18th, I can't count. 1700s, but that's the 18th century, right? They pretty well understood that this work done by these characters on the cubic and the quartic. And they're like, oh, right, so what's next? What's next down the line? Well, what are you going to do? You're going to try to solve this thing, right? If you can solve the quartic and you can solve the cubic, surely you can keep going, right? Maybe you can find a nice solution to this thing in general. After all, this is what's called the quintic, right? I can certainly do it in special cases. For example, I think we can all solve this one. X to the 5th minus 1 equals to 0. What are the solutions to that? You can tell me one solution right off, right? So x equals to 1. There are actually 5 solutions. I can draw them for you. That's a bad picture. These are supposed to, I can't do it. I'm trying. That's supposed to be a pentagon. If you look at x equal to e to the 2 pi I over, I wasn't going to do this today. Oh, well, it's too late. E to the 2 pi I over 5, e to the 2 pi I over 5, that's a solution to that. Some of you don't know what e to the 2 pi I over 5 means at this point. That's okay. We'll talk about that another day. But anyway, so you can, and those, by the way, are still pretty nice numbers. But anyway, so, there's hope. There's certain ones you can solve. And this Lagrange character in particular, and Euler, they took a really, really hard look at solving the quintic in the late 18th century. And the general techniques, they were able to understand what had been done by Tartaglia and Cardano and these guys in a sort of systematic way. And the machine that they built to understand those things just didn't seem to work in the 5th order case. So by the end of the 18th century, we started to think, I don't know, maybe there isn't a formula for the quintic that can be expressed in terms of these radicals and closed form radicals and divisions and so forth, like the quadratic formula. And in fact, it was the case that's actually what happened. Ruffini, in 1799, and then again in 1813, gave some sort of proof. Some people would put quotes around that because it doesn't seem like his proof had errors which we're not sure how to repair. I'm not a scholar on that, so I can't be sure. But so Ruffini did something. He basically said, yeah, it's impossible. There's a reason Lagrange couldn't do it. It can't be done. But then it was left to Abel, or Abel, depending on where you're from. Let's see here. When did he do this? Some numbers for you. Age 19, he gave a complete proof for the non-existence of the quintic formula. Age 19. How many of you are 19? Shame. Age 19, 1821, he actually proved that there was no such formula like this possible. All right? And in the process of doing that, started a discussion, or continued a discussion, again, really largely begun by Lagrange, which was ultimately sort of capped off by Galois. Galois, a Frenchman, again a young punk. Let's see here. I'm trying to remember. 1831. I think he died when he was 20, so he wasn't that old when he did this. In 1831, Galois, he not only showed that Abel was right, that generally quintics were not solvable, he gave a specific procedure to decide which cubics you could solve in a way similar to this, and which ones you could not. And he did this by calculating certain patterns among the roots of the polynomial. He did this by inventing what we now know is a group. He's so-called the Galois group of a polynomial. He studied this thing called the Galois group. And in a nutshell, basically the story is this. If the Galois group is what's called solvable, then formula. Nice. If the Galois group is not solvable, no formula. Game over. All right. So Galois died in a duel. I think he was 20 or 21, something like that. I mean, he did this in he was very young when he did these things. And his work was largely unnoticed until about 1846 or so. Liouville came along, a much more recognized mathematician, realized what Galois had done, the significance of it, and began promoting it to the larger mathematical world. Then the middle of the 19th century was filled with just trying to unravel, really, and understand more deeply what Galois had done, in part. And so by 1870, Camille Jordan, actually wrote a textbook which exposited this Galois theory. And sorry, same Jordan of Jordan form. Sorry if that's bad memories, but if you weren't in my linear, then Jordan form is just another term to you, right? It's just, what's a Jordan form? Who cares? All right, anyway. Oh, to give you an example of one that's not solvable, here's one. 3x to the fifth minus 15x plus 5. All right. If you try to solve this, if you try to find solutions for that in terms of radicals of the coefficients in the same sense as the quadratic formula, you can't do it. Now, the details of that are even in your textbook. If you look at I got this from your textbook. This is from page 559. That is the next to last section in the textbook. All right. So, I suppose the idea is you guys are patient, right? You're going to work through the whole textbook, and then at the very end, you're going to find out the most exciting application of group theory. Well, I think this is a very exciting application, personally. There's so much more. This Galois theory, when you get into it, it generalizes. You know that trick you guys learn in high school algebra about how to move a radical from the denominator to the numerator? That's that rationalization trick. Galois theory generalizes that to other radicals. Like if you had like 1 over something plus the fifth root or something, Galois theory would give you a way to move the radical upstairs in some kind of systematic way. It has that kind of manipulative skill. Anyway, we're not covering Galois theory. This is not a course in Galois theory. Galois theory is much more sophisticated, in fact, than what we're going to cover this semester. But I think it's important to understand that the birth of group theory really is with Galois and studying the problem of solving the quintic, right? It's not just that somebody came along and stated the definition, which I'm about to state, and said, oh, this is really cool. We should just look for, really easy examples that we can all understand. I mean, that's not how it happened. I mean, we started with this difficult problem, and this structure popped out of it. Now, the other main driving force towards studying groups came a little bit later in the 19th century with the study of transformation groups. Mathematicians like Lie, like Sophus Lie and Klein, were interested in looking at transformations on some space that left certain objects invariant, so-called symmetries, right? And we will study those in here in much more specificity. All right, Galois theory is a little bit too difficult for the first course, in my opinion, so I'm not trying to do that. All right, so this definition apparently was maybe clear in 1883. Dike and also Weber. Dike gave this stuff. Well, I don't know if he gave this definition, but he emphasized a point in the. Oh, that's not me. A point in the definition. I'm waiting for like a care package, like with like one of those, you know, yeah, with parachutes or something. Sorry. This actually, I mean, one of the points, the invertibility axiom, apparently came up in some paper about tessellations of all things. But anyway. All right, anyway, here it is. A set G with an operation star, which is actually a function, okay? Now, I said operation. You could say it's a binary operation if you like. But that's, of course, implicit with writing what I just wrote. This thing I just wrote here, right? I'll underline it in a different color here in just a moment. What is that? What is that notation implicit? What does that mean? When you write a symbol, colon, some set, another set, an arrow between. What's that mathematical code for? Or if you're an engineer, you might call this jargon. But I would disagree with you. Engineers say jargon, what they really mean is math they don't understand. Anyway, yes?
So is that saying that that operation maps the ordered pair of two numbers in G, or two elements in G, into an element in G?
Right, but maps, yeah, maps is the right word. In particular, it's a single valued assignment from each element in the Cartesian product of G with itself to G. It's a function, right? So that's the critical thing here. There's no way it can go anywhere but G. So what I just underlined in red is often promoted to be its own axiom, right? You could call it axiom 0 if you like in here. Some people refer to this, of course, as closure, right? The group operation. It's a binary operation. It has to close back in the group again. But in addition, we have three things. First, we have associativity, which means that A star B star C makes sense, whether or not I add parentheses, but let me add some parentheses here to be clear. All right, you can either do the first two and then the last one, or the last two. I mean, the order of multiplication, or the order of operation, I should say, it doesn't make a difference. 2, identity. So what that means is that there exists E in G such that what? A star E is equal to A is equal to E star A for all A in G. To be clear, the associativity, this has to be true what? For what? For all triples in G, right? And then finally, invertibility. What's invertibility say? Invertibility says that for each G in the group, there exists H in the group such that what? G star H is equal to E is equal to H star G. So we have associativity, identity, and invertibility. All of these things for an operation which is a binary operation. Now I've been saying the word operation, right? For specific examples, this operation will usually either be thought of as a multiplication or an addition. I suppose there's more. There's more other there's other examples out there, of course. I mean, we can look at groups of functions where the operation is composition of functions. All right, that's another example comes to mind. We're going to be looking at tons of examples of this. All right. One other just term here before I get into the examples, though. We say G is abelian or commutative if what? If A star B is equal to B star A for all A, B in the group. Right? If there's even one pair of elements in the group for which A times B, excuse me, A star B is not equal to B star A, it's non-abelian. All right? And again, this is of course, in recognition of Abel, or Abel, depending on where you're from, who had a lot to do with the birth of group theory. Okay. So let's see here. Let's look at some really simple examples just to get started here. Example 1. Let's look at G. Now, I mean, you notice I say a set with an operation. So like if I want to capture this idea succinctly, I might say something like this. I might say that G with star is the group, because it's a set and the operation. A given set could be given different operations in principle, all right? And those different operations would produce different groups. It's not just the set itself, it's the set plus that structure. So anyway, just comment there. So if we look at the integers with addition, right? Does this form a group? Well, yeah, I think so, right? First of all, is there closure? Certainly the sum of integers is again an integer, right? I think we can agree on that. How about if you have A plus B plus C, is it equal to A plus B plus C, so to speak? If I add A and B first, or if I add B and C first and then add A, which does it matter? No, those are equal, right? Addition's associative. Certainly 0 is an integer, right? And we do have that A plus 0 is equal to 0 plus A, right? Which is A, right? So it's associative. There's identity. Inverse, right? If x is an integer, then minus x is also an integer, right? And certainly x plus minus x is equal to 0, which is equal to minus x plus x, right? Beyond that, of course, integer addition is abelian, right? 3 plus 5 is 5 plus 3. You know this, right? You're like, this is a 400 level math course. You didn't define what an integer is. That's right. I didn't define what an integer is, and nor am I going to. Why?
Wastes time.
It wastes time is one way to look at it. Not a complete. It's what?
Is it not a defined term?
No, integers can be constructed from set theory. You can start with this successor function and build natural numbers from the successor function and various games played with the empty set. And then you can add minuses through some sort of equivalence relation nonsense. And then you can build the rational numbers. Oh, wait a minute, we're not doing rational numbers. But you can build them. But the techniques used to build them are essentially abstract algebraic in nature. So it would be kind of silly to do those at the start. We might do some of those things as we go on. All right? But for the moment, I'm assuming that you know what an integer is, which means that you assume that their standard properties hold. For example, those. Okay? So that's our sort of our MO. Same for real numbers, same for complex numbers, same for rational numbers. All right? We know what those things are in terms of their standard properties. I could construct them, but that would actually be sort of artificial at this point. So we're going to take a slightly formal view in that regard. All right. All right, so examples are important, but non-examples are also very powerful. So can you tell me something that you could do with the integers which would not give you a group? So yeah, how about example 2? How about z with subtraction or z with multiplication? Yeah. So I mean, we do have that a minus 0 is equal to minus, let's see here, how would it go? Oh, it's not, that's not even true, is it? Oh, shnikes, we don't even have that. Yeah, I don't know. I'm not sure. So subtraction is kind of a, well, certainly it's not associative, right? Think about subtraction. Is subtraction associative? If I do, for example, 3 minus 5 minus 7, is that equal to 3 minus 5 minus 7? No. Subtraction is not associative. Multiplication. Well, multiplication, there's a 1, right? A times 1 is equal to 1 times a, which is equal to a. So that's the identity, right? And it's certainly associative. A times b times c is equal to a times b times c. I need to say a word or two about notation here before I get much further. So it is associative. It's got identity, but like you said, the inverses are the problem for multiplication, aren't they? So for example, if we try to solve 2x equals to 1, so apparently 1 is the multiplicative identity. So 1 is equal to e here, right? As we think about the integers with multiplication possibly being a group. So we're gonna, I mean, we're pretty good. We got a lot of it, right? We've got closure, we got associativity, we got identity, but invertibility is where we fall for multiplication and the integers, right? Because 2x equals to 1 has no integer solution, does it? What's the solution? Right? This is, you're like, but you didn't construct a half. What do you know? What are you doing? How do you know that? Because we know what rational numbers are, folks. So we're allowed to do this, all right? Just trying to set for you the parameters of the course as we're currently. I know, because you guys, I've also been in advanced math courses where I wasn't sure what the rules were, you know? So I'm trying to communicate some of that to you. We know integers, rational numbers, real numbers, complex numbers, and we're allowed to use properties of those that are known to us from other courses. Within reason. If you've had a course in number theory, I don't want you using high-powered theories and high-powered theorems you happen to know from number theory just yet. Okay? I would throw that out. Yeah.
So for this one, the inverse.
Excuse me.
Sorry,
Oh, you're fine.
trying to think through it. So we picked an E that was in G, and we picked a G that was in G, and we showed that there's not an H, such that so basically for the invertibility, we're assuming that E is also in G. Is that kind of?
Well, E is, yeah. Oh my goodness, I'm running short on time. E is a fixed, we're about to prove E is unique, okay? So once I know that E is 1, I have to solve this equation.
Okay.
I have to be able to solve it for each G, right? For each G. Mm-hmm. And so the fact that there's even one that it fails for, it throws the rest under the bus.
So you can just pick an E.
Yeah. All right, so I'm going to move on here. Another important, okay, so examples. I get carried away with talking about things that don't matter. I forget to stay on track. Back to work here. Uh-oh. All right, so other examples. The rational numbers, the real numbers, the complex numbers, the non-zero integers. All right, so this notation, so if I take a set and put an x up here, This is what this is like, it's S in S such that S is not equal to 0, okay? It's like a standard notation. You just throw out 0 from the set. So like non-zero real numbers, non-zero rational numbers, non-zero complex numbers. These guys all form a group, right? With respect to multiplication. All right. We don't have that problem that we faced for the integers, right? And of course, we already know that this fails, right? No. Because 2x equal to 1, no solution in here, right? So the integers with 0 thrown out do not form a multiplicative group, right? We could have also picked on 0 in this example. If we took a close look at 0, we would have found out other problems with this. The fact that 0 is in here monkeys with the fact that multiplication forms a group. Big time. All right. Anyway. All right, so let me give you at least one more interesting example. Let's see, I guess this is example 3. I'm not sure what the numbering is here. Sorry. Anyway, this is technically example 1.1.9. GL NR. All right. I won't write too much here. I'm just going to mostly talk. So what this is this is A in Rn by n matrices, such that what? Such that the determinant of A is not equal to 0. All right. Now, that, and what's the operation? That's a set. Now what's the operation that I'm going to propose? You guys have had linear algebra. You know how to multiply matrices, right? Multiplication, I can't spell, anyway. So what's the, is matrix multiplication, if you multiply 2 square matrices, do you get back a square matrix? Yes. Is matrix multiplication associative? Yes, it is. Is the product, what does this make the matrix, by the way? It makes it an invertible matrix, doesn't it? Right? So as you may recall, the product of invertible matrices is invertible, right? And so, I mean, basically, most of the claim here that this forms a group stems from the following identity. The determinant of A times B, right, is the determinant of A times the determinant of B, right? So if this is non-zero and that's non-zero, of course this is non-zero as well, right? So that gives us closure, right? In other words, if A and B are elements of GLN, that implies that the product AB is an element of GLN. And you can go through and verify the others. I have a little bit more in the type notes, but I'm gonna move on here. So this is an important example. If you replace this R with Q, does this still work? What about the complex numbers? What if I look at matrices of complex numbers? Are these things still valid? They should be, yes. In fact, they are. Let's mess with it. We'll say more about that another day as we come back to these matrix examples. Just wanted to throw that out there. It's an important class of groups, things like this. That's more in line with, for example, the work of Klein and Lee, transformation groups. These matrices, of course, correspond to invertible linear transformations, which are a kind of symmetry operation. The thing that's preserved is the linear structure, all right? Okay, so our first theorem. So these theorems are from chapter 2 of Galilean. And here's our first theorem. In a group G, there can be only one element. All right, so, oh, one element, good grief. Something's missing here. Identity element, yeah. Sorry, I lost my identity. It's always confusing. Let's see here. It's almost like that was on purpose. Let's see here. Proof. Let's see here. Okay, so how would you prove something like this? You want to prove something? Okay. If you want to prove uniqueness, the way I see it, you got two main, maybe three. Sometimes you can write a formula, and the formula is just demonstrating uniqueness explicitly. We forget about this sometimes, but that's an option. The other way you can do it, of course, is to suppose that you have two, right? And show that they're equal. The third way is to suppose otherwise and show it's crazy. We will be choosing option 2 today. So suppose, by the way, I used star to denote the operation to start with, right? But what are we doing? I mean, I have been using, for example, here I just used juxtaposition, which is just writing things next to each other to indicate the operation, right? So like this is playing the role of A star B. Over here I was using plus, right? Plus is playing the role of star. So the star I wrote at the start is trying to capture the concept, right? But notationally, for specific examples, we use what notation is most appropriate. If you use plus, the group had better be commutative. Otherwise, you're just not being nice to the reader, all right? So, plus is for commutative things. Juxtaposition or star, other things, doesn't have to be commutative, of course. But as a matter of common decency, use plus for commutative things. Okay. All right. So suppose E and E prime are identities for G. All right, so what we know? We know that EA is equal to A is equal to AE. And we also know that E prime A is equal to A is equal to AE prime. These identities, are given to us by the definition of what it means for it to be an identity, right? Both of these facts are true for all A and G, right? If you know something is true for all A and G, this is going to be there's no way I can get everybody to shut up as they're passing classrooms, is it? No, it's pretty much impossible. All right, so what we want to do then is we don't care about, in fact, all of the data we have. All we really care about is the identity, right? So what you want to do in order to prove what we're trying to prove is just basically go, okay, I'm going to say what I'm interested in is E prime, right? The relation between E and E prime. So I look at the specific case, A is equal to E prime, and see what happens. So I get E prime is equal to E is equal to what? E prime E, right? But on the other hand, over here, what do I get? If I put A equals to E over here, I get E prime E is equal to E, right? Thus what? E prime E is equal to E, which is also equal to, oh man, what have I done?
Over there, it should be E prime E equals
I'm sorry?
On the right, it should be E prime E equals E prime.
On the left, I think it should be E prime plus E prime.
I'm going to ignore you guys. There's many, many flavor options here. You're probably all right, because there's like about 30 different ways to do this. And I had actually prepared this, so this wouldn't happen. But I see I have been unable to take my own advice. So E prime E is equal to E. What are you saying over here?
E prime is equal to E prime.
Oh, I'm an idiot. You're right. Thank you. Duh. You guys saw it from the beginning. All right, thus what? So we have E prime, we have E, see this is common to both ones, right? So we have E prime E is equal to E prime, but it's also equal to E. So therefore, the identity is unique, right? And the proof is done. Oh man, abstract algebra is so hard. Isn't it?
Not yet?
No, it's not. You guys shouldn't believe the lie. Abstract algebra does not have to be hard. I personally took this course, which is probably a little bit lower level of course than the course you guys are taking, granted. But I personally took it as an independent study. What I did was just to read Galois and take tests. I did homework. And it worked for me. I mean, I think that the text that you guys have is really fantastic. I'm not trying to tell you to skip class and just read Galois. That's not my point. But yes, sir, question?
What is
Oh, I'm just saying the proof is done. Sometimes I usually don't write that. When I write that, I mean my proof is done. Okay, anyway, I'm greedy. I want more theorems. Next theorem. Cancellation laws. So here they are. In a group, we have the following. AB equals to AC implies that B equals to C. And also, we have that BA equals to CA implies B equals to C. Right and left cancellation. All right? How do you prove this? I mean, if these are too hard, I can promise not to put them on the test for you guys. They're a good level of difficulty. Suppose AB is equal to AC. All right? Then A an element of G implies that A inverse is. I mean, here I'm assuming, of course, that A, B, and C are what? In a group. All right? Sorry if I haven't. I mean, you should write a little bit more when you write these out. I only have so much time in class, so I skipped some words here and there, all right? Please forgive me. If A is an element of G, that implies that A inverse is an element of G. How do I know that? Yeah, by invertibility, right? And what do I mean by that? In the sense that what? Meaning what? Right, but I mean what I'm saying is A times A inverse is equal to E is equal to A inverse times A, right? Where what? Where E is the identity of the group, right? And by the way, I don't have to worry about which identity it is now either, right? Identity is not a spectrum. There's a single one. All right. Oh, I'm sorry. Was that a microaggression? I'm sorry. I'm sorry. Excuse me. All right, so anyway, getting to the point. A inverse AB is equal to A inverse AC, right? I should say consider. Sorry, I'm just still nervous about the calculus 2 I'm about to teach. Consider A inverse AB is equal to A inverse AC, but by associativity, this makes sense, right? Well, I don't even know if I need associativity here, actually, honestly. This implies what? This implies that EB is equal to EC, right? Which implies what? B is equal to C, right? By the definition of what the identity in the group is. And there you have it. That's 1. So I'm a little bit rushed right now. I'll try to do some more careful proofs in future lectures or a little less frantic. The proof of 2 is very similar. I'm not going to rush through it for you, but you can see what you do. It's just almost the same thing. You say, okay, well, A is in the group, so inverse exists. By invertibility, multiply both sides on the right by A inverse, bam, right? Our final theorem for today is uniqueness of inverse. All right, if G is in a group G and HG is equal to E is equal to GH, where E is the identity in the group, right? And H prime G is equal to E is equal to GH prime, then H is equal to H prime. Or in words, the inverse of a group element is uniquely prescribed. All right, there's only one inverse for each group element. So what's the proof look like here? I'll start us out. Suppose HG equals to E and H prime G is equal to E. Thus what? Uh-huh. Which implies what? H equals H prime, right? How do I know that? Yeah, by law of cancellation. Or I think some of you just said just multiply both sides by G inverse, right? You're both right. But one of you was using theorem, and the other one was just going back to reprove the theorem. So which one's right? I don't know. These kind of judgments I can't make. I certainly would have fallen in the camp of I was just redoing the theorem every time for a long time in my life. All right, I want to point out some things just to try to wrap things up here. First of all, I would point out to you that our proof that the identity was unique did not use associativity, right? What does that say? You don't really need to write anything else for the rest of the thing. You can just watch with me. So what's that? I mean, if you look at it, we didn't use associativity. Right. If you were to take a group and remove the axiom of associativity, you'd still have uniqueness, right? So what is that called? You don't know? I'm not sure I know either. I'll show you what I found. Just give me a minute here too, because I just want to throw out a couple more words. It's going to be about 2 minutes to wrap up things here. Come on. 2 minutes, assuming this actually works. Come on. It's alive. No? Not alive? It's alive? Alive? Not alive? Ah, Windows. Hate you. Here, let me increase the ambiance. Let's see here. Come on. wake up. You can do it. Here we go. So this, guys, I found on Wikipedia. It's this great chart showing you various weakenings of the group axioms. Like if you, for example, just toss out associativity, what you're left with is called a loop. So our proof, among other things, proves that the identity is unique in a loop. No, I don't expect you to know all these things. What?
Is totality just closure?
Totality is closure, although it has some kind of fine print there. Now, so getting back to my larger story, you know, other things happen in terms of abstract algebra beyond group theory. You know, Euler, Lagrange, they were also looking at questions in number theory. Abstract algebra really was number theory up until about 1920 or so, probably. And the other main development was in what is called ring theory. All right, a ring is a set with two operations. You have an addition and a multiplication. So basically, here's the definition of a ring. You have an abelian group under addition and this multiplication, which has to satisfy these distributivity properties. All right, this is a ring. I know, you guys know, most of you are seniors. You're well aware of the saying, ring by spring. For us, ring by October 28th. So it's a little bit more pressing for us. But this is just to tell you there's other history that's interesting about abstract algebra. In particular, rings were used well, I'll let you read this. I'm not going to besiege you with all of it. Just let me tell you this much. The other application to group theory lately has been in terms of modern particle physics. You can actually use group representation theory to build quarks and so forth for more basic things. For example, here's how you create pions from two quarks, but you guys don't know what pions are, so who cares? I mean, I barely know what a pion is. Here's if you take two quarks together, you can get these things. If you put three quarks together, it gives you like this and then that. And so you put three quarks together, you end up with these patterns down here. This is kind of an old story by now, I suppose. But put three quarks together, you get these different patterns, these different possibilities. And there's this omega minus particle. And up here, you see a neutron and proton. The neutron and proton you knew about in chemistry. And this was actually predicted about 2 years before it was discovered by Murray Gell-Mann. And then in 1964, he proposed that there were these underlying quarks that were explaining these symmetry, these patterns, ultimately through what's called group representation theory. Again, don't worry, we're not covering it this semester. I just want to point out to you, it's a lot more than just modular arithmetic and number theory. There's much, much more you can do with groups. I'll shut up. See you Wednesday.